And those are the ones we talked about with where the whole pathway is regulated. Controlling phosphofructokinase controls glycolysis. Controlling pyruvate kinase controls glycolysis. Controlling hexokinase controls glycolysis. Great. In the glycolysis direction, in the breakdown direction, that makes sense. In the gluconeogenesis direction, in the buildup direction, that's a problem. Because now you have to, each step, if you have pyruvate, you need to get over that energy barrier to get to phosphoenolpyruvate just to start building up until you get to phosphofructokinase, sorry, fructose phosphate, then you have to jump over it again. All the other reactions we mentioned are under physiological conditions close to equilibrium. So those enzymes are able to respond to changes in concentrations, right? If it's flowing in one direction, in the glycolysis direction, then the substrates are being built up, so that favors products. But if the products are being built up, then that's just equilibrium dynamics flows in the opposite direction. So enolase, if there's a lot of phosphoenolpyruvate, enolase doesn't need any additional assistance to switch directions. So the problem with gluconeogenesis compared to glycolysis is not really a chemistry step. All the intermediates are there. The problem is the thermodynamic, and that's that getting from one direction to another is hard. You may recall that we talked about the comparison of kinase enzymes versus phosphatase enzymes, right? Kinases use ATP. And I'm just going to draw a substrate. And phosphorylate it, right? And so that ATP spends 30 kilojoules per mole in order for that to happen. And theoretically, if you have enough of that phosphorylated substrate, enough ADP, that enzyme can just go backwards, dephosphorylate it, and make an ATP, right? But practically speaking, that requires a set of product conditions that's so high that it doesn't happen in itself. But that's okay because cells have phosphatase enzymes. And so what phosphatases do is get that phosphate off without any ATP. A phosphate, phosphoester, they can be hydrolyzed, they use water. So look at the comparison from the substrate standpoint, from the phosphate standpoint. You have a kinase, you can take that substrate, phosphorylate it, uses ATP. You have a phosphatase, it can take that phosphorylated product and get it back to its non-phosphorylated state if it needs to. But they're not reverses of each other, because one uses ATP and one doesn't. The net outcome is an ATP is spent, right? If that thing gets phosphorylated, even if it's just for a small period of time, in order for it to be activated in time to control the program and then be dephosphorylated when it turns off, like, so a great talk on junk kinases and how their phosphorylation is controlled in their activity, right? That ATP, it's used. And this is ultimately what it's about, right? Cells need ATP, they make it. You're not always going to be able to recycle it. So this is the use of the ATP. But the trade-off is the kinase and the phosphatase, because they don't have the same substrates, all told, they can operate at the same time, at the same system, at the same conditions, because they're fundamentally different enzymes. They just share some features. So you can have a kinase operating under the exact same conditions as a phosphatase for the same substrate product. And that's fine. ATP will get spent, but both of those are active and they can be controlled in their own way. You understand this reciprocality. That's how in glycolysis versus gluconeogenesis, those highly energetic steps are overcome. Started backwards, right? Pyruvate kinase takes phosphoenolpyruvate. That's the highest delta G0 that we showed for a phosphorylated compound, and uses it to make pyruvate and ATP, substrate level phosphorylation. Gluconeogenesis, pyruvate kinase is not involved at all. Still get phosphoenolpyruvate from pyruvate, but you go a different way to get there. So it can happen at the same time. Or at least it's very easy to switch. You don't need to use both enzymes. Now, in the case of phosphoenolpyruvate, it's generated, it's so hard to make in the reverse direction that there's actually two enzymes needed. So when we're doing gluconeogenesis, we're talking about bypass enzymes. Pyruvate kinase is bypassed in the gluconeogenesis direction. It's only for glycolysis. PFK, phosphofructokinase, is bypassed in the gluconeogenesis direction. It's only needed for glycolysis. And the enzymology background of me really wants to go through the bioaccumulation mechanisms of all of this carboxylation stuff, but let's just keep the picture, big picture, and stay focused on the details. For pyruvate to be converted to phosphatidylpyruvate, two enzymes happen. One, pyruvate carboxylase, uses ATP to take that pyruvate and it sticks a carbon on it in the form of CO2, right? So we have CO2 that's added to the methyl group to make oxaloacetate. And the hydrogenase oxaloacetate. In gluconeogenesis, I'm going to glide through this. Biotin, again, look at your cereal box to see how much biotin you need every day. What does biotin do for you? It helps carboxylate substrates. It helps fix CO2s into substrates that need to be carboxylated. Again, think about what they're, a lot of these cofactors, I've mentioned this, but I'll reinforce it. They're present because they allow a certain kind of chemistry to occur. NAD allows for what? Reduction. And what kind of reduction? Remember, what are the electrons being carried? What's that called?
Activating payment.
And the electrons are in the form of a H2 minus hydride, right? Hydride transfers. Hydride transfer redox reactions. FADs, we're going to get into more detail, but it can be hydride transfer, but it can be 1 or 2. All right. Biotin's for carboxylations. If an enzyme, if a pathway needs to carboxylate something, it probably has a biotin-dependent enzyme in it. Again, we can go through the organic chemistry of how this works and the arrow pushing and all that. But what's cool about biotin is it's a cofactor that's post-translationally modified onto its enzymes, onto lysines. So you see that a biotin has kind of a long hydrocarbon chain of carboxylate, and it's attached to lysines. So what you get are these sort of biotin arms that in these enzymes, you end up with kind of like a biotin kelp forest flowing around from like one active site to another, where it can partition, say, the biotin activating steps with the carboxylation steps, and we see that in the carboxylase enzyme because it basically needs to be charged with biotin. So it has an active site that does that reaction, charges it onto the biotinylated portion, and then in a separate domain of the protein, that's where the pyruvate actual carboxylation occurs, right? So essentially what happens is CO2 plus ATP gives you the biotin, and then that migrates over here, and yellow, this one green, and so you get pyruvate in and LAA out. I guess, I'm not drawing, I put the ATPs over there, but, right, you see the reaction. But the reaction takes place in 3 separate stages, in 3 separate parts of the protein, and the biotin cofactor serves as this, like, go to the factory floor and you have the robot arm taking one piece from one part of the assembly line to the other, right? It's the physically mediated. Super cool from a structural standpoint.